This is a short movie to explain the concept of the conservation of angular momentum. Now, angular momentum is the quantity of angular motion that an object possesses. Perhaps surprisingly, you might think that the rotational speed of an object directly relates to its angular motion, but angular momentum is more than that. Angular momentum does involve an object's rotational speed, but it also includes a factor due to what we call the moment of inertia, the reluctance of an object. We'll look at that a little bit later. But the first thing just to recap on is how we actually get angular momentum. So the rule here is that you must have an external torque or moment of the force applied to an object. So if we consider a gymnast who's going to perform, say, a back somersault, during the period when the gymnast is on the floor, she or he must generate an external torque about their centre of mass. So the centre of mass is the axis about which the gymnast is going to rotate. So relative to this axis, the ground reaction force, which you can see in this diagram here, has to act in front of the centre of mass, which generates a clockwise rotation, clockwise torque, as we're looking at it on the movie. Now, the gymnast must generate this torque which creates the angular momentum whilst they're in contact with the floor. Once they've actually left the floor, then the situation changes. Now, in the absence of an external torque, conservation of angular momentum occurs. So when the gymnast is in the air, there's gravity and there's also air resistance, but we'll ignore air resistance. We'll consider that to be negligible in this situation. Clearly we can't ignore gravity, but gravity acts through the axis and therefore is not an external torque generating force. So whilst the gymnast is in the air, there is no force that can actually create angular momentum. In other words, the angular momentum is conserved for the period of flight. So if we were to represent that on a diagram, so here's a graph for a period of flight for a gymnast, and we can actually add a diagram here of the gymnast. So what we actually have is the gymnast having just taken off. So if we assume that this diagram here, the gymnast has just left the floor, and we assume the end diagram, the gymnast is just about to land. So this diagram represents 5 positions where the gymnast actually is in flight. For this period, the angular momentum, the quantity of angular motion that an object has, will actually be conserved and will remain constant. However, you can perhaps imagine that when you're looking at gymnasts, they don't appear to rotate necessarily at the same rate throughout the event. And indeed, if we just have a look at the angular velocity, so angular velocity, you can think of this as being the angular speed of the gymnast. We can see that's relatively low at the beginning and at the end, and relatively high in the middle. Remember, this all the time, this is in a situation where the angular momentum itself is remaining constant. So the gymnast's rotational speed is changing, so slow, fast, slow, but their angular momentum is remaining constant. And the explanation for how the gymnast can vary their speed comes when we look at the moment of inertia. So if I now overlay the moment of inertia graph, now remember that the moment of inertia is the reluctance of an object to change its rotational state of motion, and the value for the moment of inertia is dependent on how the mass of an object is distributed relative to the axis of rotation. So in this case, the axis of rotation is the gymnast's or passes through the gymnast's centre of mass. So where the mass is distributed away from the axis of rotation, as at the beginning and at the end of the move. So the moment of inertia is high, and in the middle, where the mass is distributed close to the axis of rotation, then the moment of inertia is low. So as the gymnast varies their reluctance factor, so high, low, high, so there's a corresponding change in rotational speed. So high moment of inertia, low angular velocity, low moment of inertia, high angular velocity, and all the time the angular momentum remains constant. And we can actually see this in represented in a well-known equation. So here's the equation here, where h represents angular momentum, I moment of inertia, and what looks like a curly W, Greek omega sign, represents angular velocity. So if this side of the equation remains constant, if you change the moment of inertia, you change the I, then the angular velocity must change. So gymnasts, in a variety of ways, particularly in events in diving, gymnastics, trampolining, exploit the fact that whilst they have a fixed amount of angular momentum whilst they're in the air, they can change their body shape and so change their speed of rotation. However, they can also do a little more with their body to help exploit angular momentum situations. Now, what we've got here is a video of a gymnast performing on a beam. And if we just look at that video, we'll see the gymnast generates angular momentum while she's actually in contact with the beam, has a short flight period, then once again comes in contact with the beam, and another short flight period. Now, it's the flight period that actually we're interested in here. How is the gymnast using the conservation of angular momentum in a situation like this? Well, the gymnast, obviously on a beam, when they're doing a back somersault, needs to be able to see their beam as they're coming into land. And so what you see is the gymnast trying to keep their head still. Now, it might not be apparent how they can actually do that when they've got a fixed amount of angular momentum. But if we just go back in the video and have a quick look at this portion coming up here, I'd like you just to watch carefully in the next few seconds what happens to the gymnast's head. Can you see that during the second half of the flight, the head remains in a relatively still position to the beam? So what's happening here? Well, the gymnast does indeed have a fixed amount of angular momentum, but cleverly she moves all of the angular momentum into her legs. So whilst the total amount of angular momentum in her body is constant, it's actually located during the second half of the flight in her legs, and therefore her trunk remains relatively still. So just watching this portion of the video again, so here you can see her head is relatively still, which enables her to spot the beam and land successfully. Okay, now angular momentum and conservation of angular momentum is used in a whole variety of different sports. I've already indicated that the gymnastic sports, such as diving, gymnastics itself and trampolining, are perhaps common examples, but you can also find applications in many other sports, including hitch kick in long jump, and I'd encourage you to go away and actually do some research and find out how conservation of angular momentum can be exploited by sports people. This is the end of this movie.